Main topic of chapter 3 has to do with mass relationships in chemical reactions. And one of the first things we discussed in this chapter was mass percent composition. So what's the mass percent composition of each element in propane? What mass of carbon is contained in 454 grams of propane? Well, we need the formula for propane, and then we need the molar masses for each one of the elements. So 1 mole of C3H8 contains 3 moles of carbon, 3 times the 12.01 grams per mole for carbon, and it contains 8 moles of hydrogen. So 8 times 1.008 grams per mole for the hydrogen gives us a mass of 44.09 grams as the mass for the entire molecule. And then to calculate the percent for each element, so there is 3 moles of carbon, and then each one of those carbons weighs 12.01 grams. So 3 times the 12.01 divided by the mass of the entire molecule, 44.09 times 100, gives us 81.71% carbon by mass. We do the same thing for hydrogen. Again, there's 8 hydrogens, and each one has a mass of 1.08, and we divide that by the mass of the whole molecule, multiply it times 100. A good check that we have here is if we sum these together, so all the pieces of something added together have to give us the whole thing back. So if we sum these two numbers together, we get exactly 100% back. Next, we'll see what we can do with these numbers. And so if we are told that we have a certain sample of propane that weighs 454 grams, we're now going to use this number that we just generated. We know that for every 100 grams of propane, it contains 81.71 grams of carbon from the definition. And so now the grams of propane are going to cancel, and this tells us that 371 grams of that 454 gram sample come from carbon. All right, this is now we're going to go the opposite direction. So we're given information about percent by mass of carbon, hydrogen, and chlorine in a sample. So sample's been analyzed and it's shown to have these percent by masses of each of these elements in it. We want to determine the empirical formula. A trick that we can do right away is there's not much we can do with a percent. So if we say this is exactly 100 gram sample, then the percents transform into grams. So that if we had 100 grams of this sample, it would contain 19.81 grams of carbon, 2.22 grams of hydrogen, and 77.97 grams of chlorine. Then with those in hand, we can use the molar masses from the periodic table to calculate the moles of carbon, the moles of hydrogen, and the moles of chlorine. Well, we're not quite there yet. You'll remember for our empirical formulas, we want an integer, just a simple counting number like 1, 2, 3, 4, 5, not these strange decimal numbers. So the thing that you need to make sure to do here is do not round these numbers. Do not take these numbers and round this to 2 and 2 and 2. That's not what you want to do. You want to follow this next step. You want to simplify these ratios first. So I take all of the numbers and divide by the smallest number of moles, which is the 1.649. And for the first one, that gives us exactly 1. For the second one, that gives us 1.335. And for the third one, that gives us 1.333. This is one of the times now we have to look for obvious fractions. And so we could represent this very nicely as 1 1/3, also known as 4/3. So this 1.333 could be 4 over 3, and likewise this could be 4 over 3. So 1.33 is about 4 over 3. And so 1 carbon to 1.33 hydrogens to 1.33 chlorines, or let's multiply all these through by 3 to give us C3H4Cl4. So we must have a whole number integer ratio at the end. All right, well, we've seen this graphic in chapter 2. I'll show it again, but add a little bit of information. So the empirical formula is always contained in the molecular formula, and it's contained an integer number of times. So 1, 2, 3, 4, some counting number of times the empirical formula is contained. Well, before we just could see it, so the molecular formula here is C3H6, the empirical formula is CH2, but the mass actually tells us the same story. So the mass of one of these fragments is 14.03 grams per mole. The mass of the whole molecule is 42.09 grams per mole. And so that the mass of the empirical formula is contained in the mass of the molecule 3 times. And so there's 3 of those CH2 units. And we don't write it this way though, we write it all together. So there's 3 carbons and 6 hydrogens. C3H6 is the formula for this molecule. So let's do it in a little bit more formal way. So the molar mass of the compound divided by the molar mass of the empirical formula will be X. It could be 1 if it's contained exactly 1 time, 2, 3, 4, but it won't be a decimal, it won't be a fraction, it will be an integer. So here's an empirical formula. This would need to be provided for you, or data to get to it would need to be provided. Here I'm providing the empirical formula, C2H5N. And then you would do this with your periodic table. You would take this fragment and you would calculate its mass, in this case 43.069 grams per mole. The piece of information here in blue also would have to be provided for you. So in the problem, it would tell you that the molecular mass was 129.207 grams per mole. What you would do is you would divide, it's always the bigger number divided by the smaller number, the 1.29207 by the 43.069, and you get 3 out of that. So the molecular formula is contains 3 times the empirical formula. And so the correct molecular formula for this is C6H15N3. So I just tripled all of these. 2 becomes 6, 5 becomes 15, and 1 becomes 3. So it's contained in there 3 times. Okay, the molar mass must be known, and being known means that we need to provide it for you. All right, after that we talked about balancing chemical equations, and if you have a favorite way of doing this, that's fine. I showed this formal approach that's a really fast way to balance chemical equations, and if you want to use it, then you should. So you take an unbalanced chemical equation like the one that's given here, and first you look for whatever is the most complicated species. And I would argue that this one is. It has 3 types of atoms, and in total it has 8 total atoms in it. So I would put a 1 here. Okay, so I put a 1 there just to tell myself I've looked at that one. Hold that at 1 for now. After that, I would just start balancing elements on the other side against it. And so the first thing that I hit here, bromine, shows up at as 1 product and 1 reactant. So we've said for now there's 1 bromine and 1 bromine. So I'm just going to put a 1 here to remind myself that I've checked this. And I'm on purpose not looking at oxygen because oxygen is all over the place. 1, 2, 3, 4 places oxygen is in there. So we want to look at oxygen last and hope that it just kind of comes out as we do the work. Okay, now went in and balanced carbons because carbon is present only as 1 reactant and 1 product. And so right now we've said 2 carbons, and so 2 carbons, and so I put a 2 there so I know that I've touched that part. And then finally hydrogen is the same deal. So hydrogen, there's 5 hydrogens here. We've already dedicated ourselves to 1 for now, and so 5 hydrogens as reactants, 1 that we've dedicated so far as a product. So we need to get 4 from this unit. So 2 times 2 gives me 4. 1, 2, 3, 4, 5. So hydrogens are now balanced. And then finally we left oxygen alone because we want to use the elemental oxygen to balance it. And so on the right hand side here we have 1, 2, 3, 4, 5, 6, 7. Okay, I get to 7. 1 times this gives me 1. 2 times the 2 gives me 4 more. That puts me up to 5. And then 2 times this gives me 2 more, so 7. 1, 2, 3, 4, 5, 6, 7. Well, I need to get 7 out of a species that has 2, and so the cleanest way for us to do this is to use a fraction. 7 over 2. So 7 times the 2 gives me 14. 14 divided by 2 gives me 7 from this. But we don't like that in a chemical equation. We want to get rid of it. And so we do that by clearing the fraction. So we multiply all the species through by 2, and that gives us this final equation that's 2 to 7 to 2 to 4 to 4. And then if we go through and check each side, there's 4 carbons on each side, there's 10 hydrogens on each side, there's 2 bromines on each side, and there's 14 oxygens on each side of the reaction now. All right, finally, this is sort of the meat and potatoes of this chapter. Carbon monoxide and hydrogen react to form methanol. If we have 356 grams of carbon monoxide and 65 grams of H2 available, which is the limiting reagent, how much methanol can be produced, and what mass of excess reactant remains. So anytime we're given 2 reactants, we don't know right away which one is the limiting reactant. So we need to do 2 calculations just to figure out which one's the limiting reactant. And so what we do is we start with, I usually start with whatever's first, so 356 grams of carbon monoxide. And I'm going to see the amount of methanol I would get from it reacting with excess hydrogen. So convert the carbon monoxide into moles. Use the coefficients. Here there's an implied 1, and over here there's an implied 1. So for every 1 carbon monoxide, I get 1 methanol. And then finally, let's go ahead and take it to mass. So this is the molar mass of methanol. And so I don't know yet whether this number is going to be useful or not until I do the second calculation. All right, now we're going to do a test calculation and pretend that H2 is the limiting reactant. So we have 65 grams of H2, and we're going to assume that we have more than enough carbon monoxide to react with all that H2. Convert our H2 to moles. Now use the ratio for every 2 moles of H2, we make 1 mole of methanol, and then use that same molar mass again, and put all of that in the calculator, and we get 515. And so what I would do if I was doing this on paper now is, so this is going to be our theoretical yield. This number I would X out. This is not a true number that can be used for anything else, so you don't want to accidentally use it. X it out. This is the theoretical yield that we have here. Okay, so we've answered what's the limiting reactant. Limiting reactant is carbon monoxide, and also how much methanol can be produced. 407 grams can be produced. So we'll have to do a little bit more work to figure out what mass of the excess reactant remains. Okay, so CO is limiting, 407 grams of methanol is produced. Let's do the second part of the calculation. And we're going to figure out, so carbon monoxide was the limiting reagent. Let's figure out how much hydrogen it would take to react with all of this. So 356 grams of carbon monoxide, convert carbon monoxide to moles. Now we use the mole ratio, 1 carbon monoxide to 2 hydrogens. And finally, let's go ahead and convert that to mass. Okay, and what we get out is 51.3 grams of H2. I've added the word used here, because this is the amount that would be used to react with all of the CO. This is not the amount that remains, this is the amount that was used. But we have to think back way to the problem. So 65.0 grams of hydrogen is what we started with. We used 51.3 grams of hydrogen, and so 13.7 grams of hydrogen are remaining. This is probably the most difficult type of problem that you would have to do in this chapter.